Hello Internet, my name is Quinn and this is Blondihacks. I'm working on my Pennsylvania A3 switcher locomotive this week and I'm going to make the final piece of valve gear. This has been an incredible journey for this phase of the locomotive and the end is now in sight, so let's go. The final link in our very complicated valve gear chain is between the return crank and the expansion link shown here in orange. This is the eccentric rod. This is what actually creates the primary valve movement, which is then modified for lead by the combination lever. Before we can do that though, interestingly, we have to figure out what the length of this eccentric rod actually needs to be. So for that, we have to set the return crank position to close to its final correct position for proper valve timing. To do that, I'm going to make a jig that is suggested in the book. I've got this scrap of aluminum that I cut a chunk off of, and I will clean up the edges on the mill and bring it to some very accurate dimensions. What this jig is going to allow us to do is determine exact rear dead center position on the main crank pin, and from there where the position of the return crank pin needs to be. Once that's set, then we can get on with figuring out how long the eccentric rod actually needs to be. If this all sounds crazy, the reason that we're doing this empirically for the eccentric rod length is because this is the final link in the valve gear chain, and this is where all of the errors in literally thousands of places across hundreds of parts in this entire locomotive are all coming together. We don't know how all those tiny little errors are going to accumulate. They might be working for or against us in various ways, so the drawing suggests it's best to just measure the distance of the eccentric rod rather than using the nominal that is in the drawings. This little jig then is a very specific height, and it's got a little notch in it that's the exact diameter of the main crank rod pin, and that gives us a little sighting window. So what we do is we get down low and we rotate the locomotive until the crank pin is in that window, which means it's at rear dead center. Then from here, the top surface of the jig has been calculated to give us the correct surface for the underside of the return crank pin. So we just rotate the return crank around until it touches the top of the jig, and that's the correct orientation for that arm on the main crank pin. Here it is from my viewpoint. You can see how this jig works. It's very simple, but very clever, and hopefully very effective. I can now clamp down the return crank in this position, and you can see what we've done is we've created a pivot point hovering in space above the main driver that is 90 degrees advanced from the main crank pin on the main rod. 90 degrees advanced is the correct valve timing, give or take a couple of degrees, for outside admission valves, which is what we have. If this was inside admission valves, like on a later locomotive that had piston or spool valves, then the correct position would be 90 degrees behind the main rod. Now we've got that return crank set, I can make a jig that will allow us to measure what the correct eccentric rod length is for that return crank position. This is, again, a method suggested in the drawings, and it seems like a good one, so I'm going to do it. I've got this piece of scrap hot-rolled flat bar that I'm going to cut a couple of strips out of. I like this because it's the same nominal thickness as the final eccentric rods will be. I've cleaned up the edges a little bit, and from here I'm going to set them up in the milling machine to cut what woodworkers would recognize as a half-lap joint between these pieces. What I'm doing is trying to create a link that is the same overall dimensions as the final eccentric rod will be, same thickness, same overall width, etc., but can be adjusted in length. So by half-lapping these two pieces together, I can create a joint that can slide back and forth without needing to create weird offsets or anything like that in the overall linkage. There, you can see how that's going to work. So now I just need to make an adjustable way to connect those, and we'll have our adjustable link, and then we can position that on the locomotive, and we'll know how big this rod needs to be. To that end, I'm drilling and tapping one side of our half-lap joint. I'm eyeballing this to give myself plenty of adjustment room, making sure I've got roughly 50% of the length of the lap joint in travel, which will be about 10 times as much as I'm sure I'm going to need, but better safe than sorry. I only want to make this fixture once. Then the other side gets a slot milled down all the way through the center of it that will overlap with those two threaded holes. So the two threaded holes are going to lock everything together with little bolts, and then the slot will allow things to slide. I used number 5 bolts here because conveniently number 5 bolts are exactly 5/1000ths smaller than 1/8 of an inch, so it's really easy to mill a slot that's a nice close running fit on a number 5 bolt. Maybe that's not an accident. Maybe Imperial people kind of knew what they're doing sometimes. You can see that I've also drilled and reamed the ends, and those are going to be drill guides for the final rod blanks. So once we get this thing situated on the locomotive, those holes are going to be in the correct position automatically for creating the drilled holes, or the reamed holes rather, in the final pieces. So let's get this on the locomotive and establish the correct length of this arm. We need three things to be true simultaneously. The crank pin needs to be at rear dead center, the valve needs to be just about to open the rear port, and then the eccentric rod from this point needs to be a length such that moving the radius arm up and down does not move the valve. So this is effectively the neutral position of the combination lever, such that the radius arm is pivoting perfectly on it without moving the valve. As you can see there, as I move up and down, the valve is moving. So I tweak the eccentric rod length until that is no longer the case. I'm sure there's some clever formula for determining which direction to adjust this and by how much, but I just did it by trial and error until I found a position that you see here, where the radius arm moves up and down without moving the valve. It's pivoting perfectly on the combination lever, and the rear crank pin is at rear dead center. Just out of curiosity, I measured that final length to see how close I am to nominal, and I did a little math, subtract the radius of the two pins at either end, and I come up with 3 inches 43 thousandths. Nominal is actually 3 inches 27 thousandths, so I'm 16 thousandths over on this, which is pretty interesting, but, not too bad. It turns out the length of these rods is actually pretty forgiving. I think plus or minus 10 or 15 thousandths, it still works just fine. But while we're here, the next thing to do is set the positions of the valves. I wind these in and out until, with everything at the position that you just saw on the valve gear, the valve is just about to open the rear port. It's just about to uncover the rear port. And now we've got all three of those things that I said true at the same time that need to be true at the same time. Now I can actually start making those rods. I prepared 2 of these blanks, carefully numbered because the 2 rods are slightly different. More on that in a second. Using this sacrificial fixture block, I can clamp my drill guide down on top of the blank that will become the final eccentric rod. These blanks are still oversized in every dimension, so things don't have to be too perfectly aligned here. All that matters is that the holes that I'm going to drill and ream are the perfect distance apart. I'm actually just going to drill them. I'm not going to ream them because that would require pilot drilling first, and there's nothing to keep the pilot drill perfectly centered in the drill guide, and then the reamer would tend to cut into the drill guide and it might not stay centered because a reamer is a dimensioning tool, not a positioning tool. So instead, I'm drilling with the final nominal size, but because the drill guide itself is perfectly reamed, it's going to keep that drill centered, keep it from wandering, and that drill is going to cut accurately. No reamer required. This drill guide is unhardened mild steel, of course, so it would wear out eventually if you used it a lot, but each of these ends only has to survive for 2 holes, so regular mild steel is fine. I've even made drill guides like this out of brass in a pinch. Alright, so that should be it. That first blank should now have the 2 holes perfectly drilled the right distance apart for the eccentric rod on the left side of this engine. Let's get it installed and verify that everything worked out as I had hoped. Once again, with the main rod pin at rear dead center, moving the radius arm should not move the valve. And that is looking really good. So I think the drill guide worked. Now I get to do all of that again on the other side because of course they might be slightly different, and in fact probably are. Of course, I started with using the jig with the same length setting as the other side, but that did not work. The valve was moving slightly with that length of eccentric rod, so I had to go through the fiddling process once again and find the position where the valve doesn't move. And in this case, interestingly, I measured it again, and this side came out within 2 thousandths of nominal. So this side, pretty great stuff. The first side, I guess the Friday afternoon shift built that one. It's basically unknowable where that discrepancy is really coming from. If you think about the lengths of these rods, literally everything we've done on the chassis of this locomotive to this point could be contributing to that error. Everything from the position and orientations of the cylinder castings mounted on the frame, to the positions of the bracket holding the expansion links, to the length of the piston rods and the valve rods and everything in between. Even the position of the axle boxes could be affecting it. So, we've done everything as accurately as we reasonably can as we go along, but when you get to this last link in the chain, even the tiniest of errors could accumulate and work against you at this point. If you're wondering how the real locomotives dealt with this kind of thing, they weren't making 11-foot long rods perfect to the 10th. The standard engineering mantra applies: if you can't make it perfect, you make it adjustable. A couple of key links in the system would be adjustable with wedges or similar methods on the real thing. But on these models, the parts are all just too small to make things adjustable. Hopefully Heiss is in my comments and he can correct anything I just said there that is wrong. I am not an expert on the real thing. Or even these models, really. I prepared the blank for the rod with this side using the same drilling setup that you just saw. And here it is with both of them installed. I can finally visualize the valve motion of both sides all at once. So if everything's working correctly, the ports should uncover roughly the same amount on both sides for the full cycle of the entire mechanism. And that's looking pretty good. There's some tuning probably going to be needed there, but with this valve motion, the engine's definitely going to run. From here, it's a matter of turning those blanks into actual nice looking eccentric rods, and I'm going to kind of cruise through this process because it's all steps that you've seen at least half a dozen times in the valve gear so far. It's rounding the ends and it's thinning out and tapering the center and so on. The only real difference here is these eccentric rods have a little oiling boss at the top of them, so that took a little bit of care on the rotary table to create the fillets around that boss and then machine the sides of that boss. But otherwise, it's taper cuts and scalloping the sides of the rods and so on. Same setups that you've seen thus far. These are probably the smallest, highly detailed components so far. Like the Union links were smaller, but they didn't have any real detail to them. These eccentric rods are the smallest pieces that have like rounded ends and also scalloped centers and oiling bosses and so on them. For milling the sides of them to create the scallops, I used a similar setup as you saw before, but the trick with these is, again, I procedurally determined the length of these rods, so I don't know exactly how long they actually are. So I used a setup like this to have the part essentially tell me where the two fixturing holes need to be for the fixturing block. That's going to allow me to do the side milling. And of course the two rods are 14 thousandths different, so I had to do all this again when it came time to do the other rod. I couldn't reuse any of these setups, which was a little annoying, but after all of these parts, that's going to happen. I used the pins to orient the part horizontally on the jig, and then I clamped it in place. As I've shown in previous videos in this series, using little screws in the center is not strong enough to hold against milling forces, and that wouldn't be a very accurate alignment like you get with pins. Plus the pins give you a place to edge find on so you can line up the features, which is really handy. But otherwise it's a standard plunge the ends of the scallops and then side mill in between them to create the detail. I did have one unique problem with this setup on these parts. Because they are so thin, these linkages are so small, they did have a tendency to pull away from the jig in the middle. You'll see the effect of that later on. But from here, this is a technique you saw me do earlier, I think on the side rods. After side milling one side, I then mill a pocket out of my fixture block, the depth of the width of the larger end of the rod minus the remaining thickness of the center of the rod, if that makes sense. That allows me to flip the rod over and nestle the fat ends of it into the fixture block so that the interior of the rod, which is now thinner, is still sitting up against the fixture block. I can clamp it down and side mill this side. This setup also allowed me to drill the tiny oil holes that are in the tops of these bosses. There was some very careful edge finding there to get those centered, and then I drilled those through. And the other interesting thing about these rods is they have little bearings in them, so I'll make those quick on the lathe. I've had a weird influx of commenters lately who don't seem to be aware that plain bearings exist. The term bearing doesn't just mean modern mechanical bearings like roller bearings, needle bearings, etc. The term bearing really just means two surfaces that are designed and or engineered to run against each other. Roman chariots had bearings in them. Medieval farm carts had bearings in them. And yes, locomotives have plain bearings in them that are just bronze rings. A lot of people seem to insist these are bushings and not bearings, but yeah, nope. Plain bearings have been a thing for thousands of years. There's no shame in not knowing things. The shame comes in when you storm into my comments and Dunning-Kruger all over them. Now I gotta clean up that mess. Tiny Yahtzee. Those bearings then got Loctited into the big ends of the rods, and then I used a pin vise to drill the oil passages straight through, so of course the oil can get into the pin where the oil is actually needed. Here's the two final rods. Hey, what's under your hand there, Quinn? Nothing. Looks like there's another rod under there. No. Are you sure? Because I think I see it. Oh, yeah. So this one didn't turn out great. The end of it is kind of off-center because I had the rotary table misaligned on the spindle. I don't know what I did wrong there. And then in the middle of one of them, the side milling, the cutter grabbed and pulled the part away from the jig. I was alluding to that problem earlier, but all the damage is going to be on the inside of the part where you can't see it. And the wonky ends are going to be completely covered by these large flat-headed pins so you can't see them. So it really wasn't worth scrapping the parts for those little defects. It's really interesting how scale can completely alter methods that work and don't work on machining parts. I used almost all the same setups and procedures that I used on the side rods for these because they're virtually identical parts, but a lot of those setups did not work well because these parts are like 60% smaller. So the material's not as strong, not as rigid, and so I had to alter my setups in ways that I found out when it was too late. Regardless, that is moving well on there. It was a real fun job getting all those very, very tiny E-clips on there. I think I went through about 20 of them before I got 5 of them that didn't spring off into space on each side, and stabbed myself with the screwdriver about 7 times trying to push them in. And of course they're on the inside so they look nicer, which is even more of a challenge. I don't have a better idea for how to secure these pins, to be clear. I think E-clips are probably the best way, but boy, it sure is tricky to get them in there, let me tell you. As I said before, all of those pins have been hardened, so they're a nice bearing surface for the mating parts. Well, there it is. There's the full valve motion. It's kind of motion blurry here as I roll it past the camera, so I'll set it up on a stand here in a minute for you to see, but it's better to see it with the weight on the suspension. Just like a car, the driveline gets a little weird when the wheels are dangling in the air, but here's the same valve motion stationary. What I really need to do is build a rolling road so that I can have the weight on the suspension and have the wheels turning like this. And that will be necessary for running it on air. You don't really want to run it on air with the wheels dangling because the suspension will flex and create weird side forces on the linkages that aren't supposed to be there. Makes it harder to set valve timing and so on. So this is what it's going to look like though. It's pretty cool to see it in action. You can see the full valve motion there from the return crank plus the lead being created by the combination lever. All of which you immediately understood because you watched my video on Walshart's valve gear, didn't you? Yeah, that's what I thought. Well, it sure looks cool anyway, even if you don't understand it. That testing revealed one interference, though. The lower corner of this combination lever on one side only was just kissing the crosshead guide rail on the underside at full back stroke of the lever. One of my patrons who is also building this engine and had modeled it all out in CAD warned me that this linkage really does not have enough clearance under it, and he is right. I increased the clearance beyond what Kozo had, but not as much as my patron had shown me. And, well, I had to file a little bit more out to get it to clear on that side. It's very, very close in there. Really too close. But otherwise, everything is looking and running great. We are basically ready to run this thing on air. It's now capable of running on air. However, I do need to do a little bit of prep work before we can actually do that. Like I said, I got to build a rolling road. Got to do a few other little things. We got to adjust the pistons. So a little more work to do. I'm sorry, you're just going to have to wait a little bit longer and then we'll all get to see this thing chooch for real. Thanks for your patience. Thanks for hanging in here with me. Thanks to my patrons for making this happen. And I'll see you next time.